So you'll be having about that. So good morning to all. You'll be seeing about that magnetostatics. Okay, wow. So in the last one we have seen about the that electrostatic fields. Today you'll be seeing about the concept of magnetostatics. Okay, wow. So you'll be seeing about the magnetic field concept here. You'll be seeing about that magnetic field concept. Okay, wow. So first we will be comparing the electrostatics and magnetostatics here. So in terms of electrostatics, we call it as E, whereas the magnetostatic field, we have magnetic field intensity, which we call it as H. Similarly, in the electric field, electrostatics, we have the electric flux density, D there. Okay, so hold on a minute, pa. The next one we'll be having as the in electrostatic field we have that permittivity epsilon. Whereas when you see with the magnetostatics, you will be having that permeability mu there. And the basic comparison of electrostatics with the flux density and field intensity, we have that D equal to epsilon E. Whereas when you go with that magnetostatics, we will be having with B equal to mu H there. B equal to mu H, where B is the magnetic flux density and H is the magnetic field intensity. This is a basic comparison between that electrostatics and magnetostatics. So in the Biot-Savart's law, mainly they will be asking that get part. So by giving that I value and a R value, you'll be asked to calculate the magnetic field intensity. So what is that DH? DH is nothing but magnetic field intensity. So it is directly proportional to product of the current element, IDL, into sine alpha divided by R square. IDL sine alpha divided by R square. So here we are inserting the proportionality constant, what we call it as K. So DH equal to K into IDL sine alpha by R square. DH proportional to IDL sine alpha by R square. So DH equal to K IDL sine alpha by R square. That K is called as a proportionality constant there. Okay, and it has a value of 1 by 4 pi. 1 by 4 pi. So when you deal with that proportionality constant, there you will be using in electrostatics K equal to 1 by 4 pi epsilon. So most of the students will be doing that mistake that they will be having with DH. Here also they will be substituting in magnetostatic also. They will be substituting DH equal to 1 by 4 pi epsilon. It is not so. Here only you will be having with 1 by 4 pi there. So clearly see that one while solving that problems in the related with magnetostatic fields. So you'll be getting the relation between flux density and field intensity. B is equal to mu H. So dB equal to mu into dH. What you'll be having there? Already know about that mu, and dH value is nothing but IDL sine alpha divided by 4 pi R square. IDL sine alpha divided by 4 pi R square. So we can also express that Biot-Savart's law in the vector form. Can also express Biot-Savart law in the vector form. So that dH equal to, will be having as IDL cross AR divided by 4 pi R square. IDL cross AR divided by 4 pi R square. Okay, in terms of vector, we can represent that. Okay, that AR vector only you will be having as R vector divided by modulus of R vector. So what you will be having that DH equal to IDL cross R vector divided by 4 pi R cube you will be having. Then about the basic concept about magnetic flux density. What is the magnetic flux density? It is a thing but number of magnetic flux lines crossing or passing per unit area. Normally the magnetic flux density is denoted as B. Magnetic flux density is denoted as B. So the unit of magnetic flux density is Weber per meter square. So we have the formula that B equal to 5 by A. So unit of magnetic flux is Weber. Unit of area is meter square. So you will be getting magnetic flux density is Weber per meter square. Okay, and also we can relate magnetic flux density and magnetic field intensity by the formula B equal to mu H, where mu is called as the permeability of the medium. Mu is called as the permeability of the medium, and it is equivalent to the mu is equivalent to mu naught and mu r. Mu naught and mu r. Where mu naught is called as absolute permeability. So in electrostatics, we call epsilon naught as permittivity, absolute permittivity. Similarly here, in magnetostatics, we have permeability. Mu naught equal to absolute permeability, and it has the value of 4 into 10 power minus 7. 4 into 10 power minus 7. So the relative permeability of the medium depends upon its value depends upon the medium used. Its values depends upon the medium used. So for free space, we have that relative permeability is 1, and for iron material, similarly, we will be having it as 1000 or 5000 like that. So it depends upon the medium used, you will be having mu r value there. And magnetic field intensity is given by the formula H equal to Ni by L. H equal to what you will be having? Ni by L here. Magnetic field intensity H equal to Ni by L. Unit is ampere turns per meter. Unit what you will be having? Ampere turns per meter. So H equal to Ni by L, where N is number of turns, I is the current passing through the conductor, and L is the length of the conductor. And L is the length of the conductor. Okay, so H equal to Ni by L. So we are seeing a small model problem relating with magnetic flux density and field intensity. Okay, where we have to find out finally the flux. You can see a model problem here. Here we have the iron ring with a cross-sectional area of 3 centimeters square and mean circumference of 15 centimeter. Is normally wound with 250 turns of wire, and it carries a current of 0.3 amperes. Carries a current of 0.3 amperes. So the relative permeability of the ring is 1500. Relative permeability of the ring is 1500. So what we have to do is we have to calculate the flux established in the ring. We have to calculate the flux established in the ring. Okay, so from the field intensity, you can calculate flux density. From flux density, you can calculate flux there. Okay, so we know that B equal to mu H. If you find out H, you can calculate B. And you know the formula B equal to 5 by A. If you find out B, you can calculate 5 value there. So H equal to I by 2 pi R. Magnetic field intensity of the iron ring. It's normally the circular coil. Iron ring will be in the form of circular coil. For that, the field intensity is given by the formula H equal to I by 2 pi R. So 2 pi R is nothing but circumference. 2 pi R is nothing but circumference. So you will be getting I by C. H equal to what you will be having? I by C. So H equal to, already know the current value 0.3 and substitute that circumference value 15 centimeter. You will be getting H value. So B equal to mu H, what you will be having it substituted. From that, if you know the H value, you can find out the B value. Flux density. So after finding out flux density, you can calculate the flux by using the formula phi equal to B into A. B is equal to 5 by A. From that, what you can have? Phi equal to B into A. Here you have calculated for the one thing of wire. So the total flux established in the ring is calculated by number of turns into flux there. For one turn, you will be getting 1.14 into 10 power minus 6 Weber. So for a total flux established ring, what you will be having it as phi total equal to N into phi. N into phi. So next we have with that Lorentz force equation. F equal to we have the Lorentz force equation gives a relation between the force with the electric field and magnetic field intensity. So F equal to Q into E plus V cross B. F equal to what you will be having? Q into E plus V cross B. So where E is the electric field intensity and B is the magnetic flux density. E is the electric field intensity and B is the magnetic flux density you will be having there. Okay, so this Lorentz force equation relates the charge and with the electric field and the magnetic field concept. The next one you'll be seeing about that Ampere's law. Okay, so according to Ampere's law, what you'll be having that line integral of magnetic field intensity around the closed path is equal to the total current enclosed by that path. Okay, so line integral of magnetic field intensity around a closed path is equal to the total current enclosed by that path. So the closed integral of H dot dl equal to I. This is the basic concept from the Ampere circuital law. You will be having that. Closed integral of magnetic field intensity around the closed path is equal to the total current. So the path should be the closed one. Very, very important thing. The path should be the closed one. We can apply the Ampere circuital law only to the closed path. We cannot apply it to the open path there. And for that, we have shown a model problem here. You can see that one. You can see the representation of the closed path. For this configuration, we have to find out the closed integral of H dot dl. So we can see that 100 amps and minus 10 amps within the loop and 5 amps is outside the loop there. 5 amps is outside the loop there. So according to Ampere circuital law, what you will be having? Closed integral of H dot dl equal to I enclosed. Closed integral of H dot dl equal to I enclosed there. Okay, so the total current is nothing but 100 minus 10 amperes. So they have given us minus 10 amperes. So you'll be getting 100 minus 10 amperes. Actually, we have to add that too. Since it is in minus sign, you will be getting it as 100 minus 10 amperes. You will be getting it as 90 amperes. So we have that 5 amperes, which is the outside the path. So it has no effect on field. That's what I have told them. The integral should, if you are taking that, the part should be the closed one. Part should be the closed one. Then the next one, what we can see with that. Similar in the second unit, we have seen about, in the last sessions, we had seen about that electric field due to finite and infinite conductor. Similarly, electric field because of circularly charged disk and all these concepts. Similarly, here also, we can find if I pass current through the finite conductor, what is the magnetic field intensity at the point which is nearer to the conductor? I am having a conductor which is having the current. Because of the current flowing in the conductor, what is the effect of magnetic field at the point which is nearer to the conductor? Instead of finite conductor, if the conductor is infinite, that we can have with infinite conductor. What is the magnetic field at this point because of this infinite conductor? Okay, so when you go with that finite conductor, definitely we have with that starting and ending. So you'll be having with alpha and alpha 2 then. The point with one angle will be having it as alpha 1, point with another angle will be getting it as alpha 2. So B is equal to what you will be having that mu I by 4 pi h, magnetic flux density. Always first you will be finding out magnetic flux density. From that you can calculate the magnetic field intensity. So B is equal to mu I by 4 pi h into cos alpha 1 plus alpha 2. Weber per meter square. The flux density has another formula, what we call it as Tesla then. Okay, so B is equal to mu I by 4 pi h cos alpha 1 plus cos alpha 2. This is for finite conductor. If you know B, we can calculate H using the formula B is equal to mu H. Using the formula B is equal to mu H, you can find out the H value. So for infinite line, we are substituting alpha 1 and alpha 2 value as 0 there. Alpha 1 and alpha 2 value as 0. So here if you substitute 0 here, what happens there? Cos 0 plus cos 0. Cos 0 is 1. So 1 plus 1 you will be getting 2. On simplifying that, you will be getting B is equal to mu I by 2 pi h, and H is equal to I by 2 pi h. H equal to I by 2 pi h, and B is equal to what you will be having? Mu I by 2 pi h. Okay, so this is what you will be having it for infinite line conductor. Similarly, if you want to find out the magnetic field intensity because of the circular current, that is current carrying conductor, circular conductor. The last one, what we have seen with the straight finite conductor. Now for the circular conductor, what will be the magnetic field intensity at the point which is nearer to it? You can see the diagrammatic representation of the circular conductor, where we have to find out the point also, it is mentioned there. The distance between the point and the center of the circular coil, we call it as H, and the radius of the coil, we call it as R there. Then after apply the Pythagoras theorem, you will be getting that x equal to root of R square plus H square here. So the magnetic field intensity or the magnetic flux density, first you will be finding out mu R square I divided by 2 into R square plus H square whole power 3 by 2. This is the magnetic flux density for the circular conductor. Magnetic field intensity. So B is equal to mu H. From that H is equal to what you will be getting? B by mu. Okay, so if you substitute that one, you will be getting H value also. Now this is a special case. So this one they will be asking you in the exam point of view. Okay, so at the center of the circular coil, what is the magnetic field intensity? At the center of the circular coil. What is the magnetic field intensity? So that means if the point is at the center of the coil, in the diagram we can see that point is somewhere located. Now if the point is at the center of the coil, what happens? That H value will be 0. H value will be 0 there. Okay, so if you put H value equal to 0 in that equation, what you will be getting that? And simplifying, H equal to I by 2R. H equal to I by 2R, ampere turns per meter here. H equal to I by 2R, ampere turns per meter. Magnetic field intensity. Okay, so you can simply calculate the magnetic field intensity and flux density. You can see that one. Determine the value of magnetic field intensity at the center of circular loop carrying a current of 10 amperes. The radius of the loop is 2 meters. So we have to determine the value of magnetic field intensity at the center of circular loop. So H is equal to I by 2R. We already know the radius value, R value. So if you substitute that one, H equal to 10 by 2 into 2. That's what you will be getting as H equal to 2.5 ampere per meter. 2.5 ampere per meter. Now so far we have seen for finite conductor and circular coil. Now for infinite sheet, in the infinite sheet, if it has a small amount of current, what will be the magnetic field intensity? The infinite sheet. So here we are representing in terms of current density. The infinite sheet which has the current. So here we are representing, to find out the magnetic field, we are representing in terms of current density. So if the infinite sheet has current, then field intensity is given by the concept of half of the current density. It is Ky by 2. Ky by 2. So depends upon the position, it may be positive or negative. So if it placed above the Z axis, that is Z greater than 0, you will be getting Ky by 2. If it is Z less than 0, you will be getting it as minus Ky by 2. Okay, then P and H on the axis of solenoid. On the solenoidal coil, what will be the value of B and H? Magnetic flux density and magnetic field intensity. It's same as that of minimum with respect to the finite length conductor. Finite length conductor. So when you go for the different magnetic materials, So what are the different magnetic materials? We are having that one. Diamagnetic material, paramagnetic material, ferromagnetic material. Okay, so the diamagnetic material will be having less magnetism property, and paramagnetic material will be having moderate magnetism property, and ferromagnetic material will be having a more amount of magnetism property. So we can define this thing, the diamagnetic material. So we have to apply the external magnetic field. So in this type of materials, the external magnetic field will be producing no torque on. Here you will not be getting no realignment. Okay, so some of the examples of diamagnetic materials, what we have it as helium, sulfur, graphite, sodium chloride, etc. Paramagnetic materials. So when you apply any external magnetic field around that materials, they will produce small torque. Okay, and the atomic moment will be produced here, and they will be aligned to the top external field. Okay, so the tungsten and all will be coming under that paramagnetic materials. Whereas when you go for that ferromagnetic materials, it will be having more amount of magnetic field. Even for small amount of applied external magnetic field, you will be getting more amount of torque there. Okay, so iron, nickel, cobalt, all comes under the ferromagnetic materials here. And as I told here, we can also classify the magnetic materials depends upon the relative permeability, mu r. Depends upon the relative permeability, we can classify the magnetic materials. If the magnetic relative permeability is lesser than 1, then the material is called diamagnetic material. It's very, very lesser than 1. If the relative permeability of the material is very, very lesser than 1, then we can say the material is diamagnetic material. Second one, if the relative permeability of the material, that is mu r value, is moderately equal to 1, is nearer to 1, we can say the material is paramagnetic material. If the relative permeability of the material is very, very greater than 1, relative permeability of the material is very, very greater than 1, then it is corresponds to ferromagnetic material. Then it corresponds to ferromagnetic material here. So you will be having 3 magnetic materials: diamagnetic, paramagnetic, ferromagnetic materials. Okay, so next we can see about the curve called magnetization curve or BH curve. We say the curve as a BH curve or magnetization curve here. Okay, or we can simply say it as a hysteresis loop curve. So on seeing this curve also, we can determine the type of the material, whether it is diamagnetic, paramagnetic, or ferromagnetic material. So this loop is called BH curve. From BH curve, we will be getting one loop. That loop is called as the hysteresis loop. Hysteresis loop. And see, with that one, we can find out the which type of material on seeing the loop. Okay, so you can see the thing here. When you increase the magnetic field intensity, flux density also increases. You can see in the diagram clearly here. I'm increasing from 0 to C there. What happens if H increases, B also increases. So after C, I am reducing H value. I'm reducing the H value, but flux density will not follow the same path, whereas it takes the new path and that ends at D there. And ends at D. This O and D is what we call it as residual flux. OD is what we call it as a residual flux. Even at field intensity is 0, we are getting some amount of magnetic flux density because of the residual flux which is present in the material. Even at field intensity is 0, we have some amount of flux density. That what we call it as residual flux. Now I am increasing the H value in the negative direction. So from D, now B value will comes to 0 there. B value will comes to 0. Here this property what we have it as a coercive force which is present in the material. Because of coercive force which is present in the material, if you increase the H in the negative direction, at one point the B will comes to 0 there. Then later on it goes to the negative maximum. So this is will be repeated for another cycle. You can see the loop here. C, D, E, F, A, B, C. This closed path will follow one loop. Once again repeating C, D, E, F, A, B and C will form the closed path. So this nothing but this loop is called as the hysteresis loop. This loop is called as the hysteresis loop. Okay, so as I told, we can classify these magnetic materials. We can see the nature of magnetic materials by seeing this loop itself. How? If the area of the loop is narrow, if the area of the loop is narrow, then it comes under the, that material comes under the ferromagnetic material. That is, it will be having good magnetism property. A good magnetic material should have narrow hysteresis loop. The area of the loop, that closed loop I told you, no, C, D, E, F, A, B, C. In that closed loop, the area of the loop is narrow. It corresponds to good magnetic material, that is the ferromagnetic material. If the area of the loop is more wide, then it corresponds to diamagnetic material. That means that material will be having poor magnetic property. Even between that one, you will be getting paramagnetic if it is somewhat extended. So in the electrostatics, we have seen about the boundary conditions. There we have seen for different mediums. That means we have placed one dielectric over another dielectric, one conductor over another dielectric, one dielectric over another free space. For that and all, we have seen about the what is the tangential component of electric field, what is the tangential normal component of electric field, normal component of flux density, tangential component of flux density. That and all we have seen there. Similarly here, we can see it for magnetic materials. Similarly here, we can see it for the magnetic materials. If you place one magnetic material over another magnetic materials with different permeability, it's very, very important. Two different magnetic materials which are having different permeability. So you can see the diagram here. Medium 1 is having permeability of mu1. Medium 2 is having permeability of mu2 here. When you place one material over another material, what will be the effect of? What will be the effect of magnetic field intensity and magnetic flux density? There we have seen about electric flux density and electric field intensity. Similarly here, you will be seeing about magnetic field intensity and magnetic flux density here. So if you place one magnetic material over another magnetic material, what happens is the tangential component of magnetic field intensity is continuous. Whatever the tangential component of magnetic field intensity you are getting in medium 1, same you will be getting in medium 2. Tangential component of magnetic field intensity at medium 1 will be same along with the medium 2. That's what we are seeing here. Okay, similarly, the normal component of magnetic flux density will be same. Normal component of magnetic field intensity will be same here. Magnetic flux density, magnetic flux density there. That is Bn1 equal to Bn2. So you can simply remember with the magnetic boundary conditions, HT1 equal to HT2 and BN1 equal to BN2. So already this concept of derivations you might have studied in your lower semesters itself. So for this gate preparation, just I'm giving the clues here. What is that? Magnetic boundary conditions. Okay, between you place two magnetic material one over the another. What will be the tangential component of magnetic field? How will be the tangential component of magnetic flux density? Okay, so here tangential component of magnetic flux density field intensity is continuous, and normal component of magnetic flux density is continuous there. This is the thing what you will be having there. And next one can go for the scalar magnetic potential and vector magnetic potential. So we know the concept that the relation between electric field and potential E equal to minus del V. The last electrostatics we have seen that one. E equal to minus del V. Relation between electric field and potential. Similarly, the relation between magnetic field and potential is given by the formula H equal to minus del Vm. H equal to what we will be having? Minus del Vm. Where H is the magnetic field intensity and Vm is the scalar magnetic potential. So I told you that we can see that you can study the equation as a statement. We can study the equation as the statement there. So the magnetic field intensity is nothing but negative gradient of scalar magnetic potential. Negative gradient of scalar magnetic potential. Okay, wow. So H is equal to what you will be having? Minus del Vm. H is equal to minus del Vm. Okay, wow. Magnetic field intensity is the negative gradient of scalar magnetic potential. Del Vm corresponds to the scalar part. Okay, wow. So H is equal to minus del Vm. Okay, so from Ampere's circuit law, if you represent in point form, we will be having that del cross H is equal to J. This can also be asked in 1 mark in the gate question. The curl of magnetic field intensity is dash, current density, charge density. Okay, so like that they will be asking you. Okay, the curl of magnetic field intensity is equal to current density. That is del cross H is equal to J. Del cross H is equal to J there. Del cross H means what? Curl. If it is del dot H, then divergence. Del H means gradient. So del cross H is equal to J, you will be getting that. The curl of magnetic field intensity is equal to current density. So the next one you will be having with vector magnetic potential. Okay, so vector magnetic potential. So vector magnetic potential. So whereas scalar magnetic potential we can use the system where you will be having scalar magnetic potential. You will be having in the system where the current density is 0. You can use where the current density is 0 there. Whereas vector magnetic potential it can be used in the region where the current density is 0 or non-zero. So normally you should know the concept that magnetic field has no divergence. Theoretically we can say that one. Magnetic field flux density, magnetic flux density has no divergence. That is del dot B equal to 0 there. Okay, so then next one we can say that one. The curl of any vector, the flux density we can represent as del cross A there. B is equal to del cross A. Okay, so divergence of curl of any vector is 0. That from that we can have it at del dot del cross A equal to 0. Already we have del dot B. The del dot and del dot will be getting cancelled. So that you are getting B equal to del cross A there. Okay, so substitute that values and you will be getting with that del square A value here. Del square A, that is Laplacian, equal to minus of mu J. Minus of mu J here. And we see a model problem here where they will be giving you magnetic field intensity and magnetic flux density. Where you have to calculate magnetic field intensity and magnetic flux density, and they are given the value of A here. A vector, that is the vector magnetic potential they are given you. They are asked to calculate magnetic flux density and magnetic field intensity. We know the formula. If you want to calculate magnetic flux density, B is equal to del cross A. B is equal to what you will be having? Del cross A. So that means you have to take the curl. That means you have to take the curl of the vector. So del cross A is equal to, since the system is Cartesian system, we have with AX and AY. So del cross A equal to AX, AY, AZ, dou by dou X, dou by dou Y, dou by dou Z. You know that AX vector 3y minus 3 and AY vector 2xy. We substitute that one, we can have it as del cross A value. That is nothing but B. Once you know about B value, you can calculate H value there. H is equal to B by mu. H is equal to B by mu. H is equal to B by mu. So in cylindrical coordinates, what we have with the cylindrical coordinates. So A vector they are given here. Okay, we want to find out magnetic field intensity, magnetic flux density, and current density J there. That is B, H, and J. We have to find out there. B you can find out with a normal formula. Just now we have seen B is equal to del cross A here. B is equal to del cross A. Once you know about that A value, so I told that the first session itself, the different coordinate system is very, very important. Cartesian, cylindrical, and spherical coordinate system. You can see this question, it is given in cylindrical coordinate system. For cylindrical coordinate system, what is the formula for curl? That we have to first determine. For cylindrical coordinate system, what is the formula for curl? So B is equal to del cross A then. So for curl, we have it for cylindrical system, we will be having it as 1 by rho, then A rho, rho A phi A Z, dou by dou rho, dou by dou phi, dou by dou Z. Then we have to substitute that coefficients there. We substitute, we will be getting the B value. Then already know about the H value, standard formula. H is equal to B by mu. So in free space, straight away you can write mu naught because mu r will be 1. So we have represented here H is equal to B by mu naught. Then current density J equal to del cross H. Current density J equal to what we'll be having? Del cross H here. Okay, once you know about the H value, we have to take the curl of the H value to get J value. If you take the curl of the H value, you will be getting J value there. So J equal to del cross H, substitute the thing, you will be getting J value here. So once again, it is in cylindrical coordinate system. While solving the curl, divergence, and gradient, see the system, whether it is Cartesian system, cylindrical system, or spherical system. Because most of you are thorough only with the Cartesian system. You should be aware of cylindrical and spherical system also. So now we can see with the differential on force on a differential current element. That what we have it as, when a current carrying conductor placed in magnetic field, you will be getting a force. That is nothing but a mechanical force. That's a basic principle of the motor. What you will be having that one. When you place a current carrying conductor on the magnetic field, you will be getting the force there. So that is given by this concept here. F equal to IL cross B. So when you take the cross product, you will be getting F equal to ILB sin theta. ILB sin theta to n cap. So in generalized form, we can say it as F equal to BAL sin theta Newton, where B is the flux density I is the current and L is the length of the conductor. And theta is the angle between the flux and the length of the conductor. Okay, so that you can see that one. Similarly, the force between two parallel conductors. The conductor 1 is carrying the current of I1 and conductor 2 is carrying the current of I2. You can see in the diagram. One is in the same direction, another one is in the opposite direction. What will be the force exerted between these two conductors? What will be the force exerted between the two conductors? So that you can see with this formula. F equal to mu naught I1 I2 into L divided by 2 pi R. F equal to mu naught I1 I2 into L divided by 2 pi R Newton. The force per unit length is that length will comes to the left hand side. Force per unit length is equal to mu naught I1 I2 divided by 2 pi R into Newton per meter. Newton per meter. Then when you go for the torque, when you place with the torque, we will be having with mb sin theta. Torque equal to mb sin theta, where m is called magnetic moment. M is called as a magnetic moment and it has a formula of NIA. N is number of turns, I is the current and A is the area of the loop. You can see this one here. The square loop, A is the area of the loop. I is the current flowing through the conductor and L is the length of the conductor. What do we have? Here with respect to magnetic moment, N is the number of turns of a conductor. So T equal to MB sin theta, M equal to NIA. If you want to represent them in vector form, we can say T equal to M cross B. T equal to MB sin theta we have. In vector form, we can have torque equal to M cross B there. You can see in this one, we have a small conductor of 6 meters long, lies along the Z direction. It has a current of 2 amperes in AZ direction. We want to find the force experienced by the conductor if the flux density is 0.08 AX. So they have given you current value and flux density. What you have to calculate is force experienced by the conductor. So they are given in vector form. So we are solving the problem in the vector form. If it is the real values, straight away you can use F equal to BAL sin theta. But here they are given in AX and AZ. So I am solving it in vector form. F equal to IL cross B. F equal to what we will be having? IL cross B. Okay, I is the current and L is the length of the conductor. That one term of 6 AZ and B 0.068 AX. So you will be getting 0.9. Why I represented AY? So it's a vector product. The vector product AZ cross AX is AY. AZ cross AX is AY. So we are having that one. Here the same model problem relating with that one. Once again, the model problem relating with force. Here you can see that one. F equal to IL cross B, same concept. The 10 AY cross AX. Actually, AX cross AY is only AZ. But we are getting AY cross AX. So AY cross AX is minus AZ. AX cross AY is what you will be having? Minus AZ. So F equal to what you will be getting? Minus 2AZ. So F is equal to what you will be getting? That minus. So this and all, they will be twisting you in exam point of view. They will be giving it as 2AZ minus 2AZ, 3AZ minus 3AZ, like that they will be giving you. Okay, so here clearly we have to see this concept. Why we are substituting minus AZ? Because it is Y cross X. AY cross AX. If it is AX cross AY, then it is equal to AZ. But here you are getting it as AY cross AX. So you will be having minus AZ. Then the thing you can see with that force per meter length of the parallel wires. We have two parallel wires A and B. What is the force per meter length? The diameter 5 centimeter. What the given distance, actually the distance and the diameter. Printing mistake we have. and the current carrying conductor has 40 amperes in the same direction. So force per length equal to mu I1 I2 divided by 2 pi d. Mu I1 I2 divided by 2 pi d. So 4 pi into 10 power minus 7. Both having same currents of 40 amperes. So 40 into 40 divided by 2 pi into distance 5 centimeter. That is 5 into 10 power minus 2. If you substitute, you will be getting force per length. Then the next model problem we can see with the torque. What is the maximum torque on 85 turns rectangular coil with the dimensions 0.2 cross 0.3 meter, carrying a current of 5 amperes. The field B is equal to 6.5 T. Tesla, capital T is Tesla there. So in the magnetic flux density, if they given with capital T, it is Tesla. So we want to find out T max. What is the T formula actually? MB sin theta. MB sin theta. So when you substitute maximum, when you will be getting maximum torque, when theta equal to 90 degree, sin 90, it is 1. So T max equal to M into B. Just now we have written that one. T max equal to M into B. M is called magnetic moment. B is called as flux density. Okay, so M we have the formula IA. Current value is given. Current value is also given. Turns also. Area is also given. We can find out magnetic moment. And flux density is also given. Straight problem can have with that T max. This is for 1 turns. For 85 turns, we have to multiply with 85 there. Yeah, this is how you will be getting. Next, we move on to the inductance. Next, we will be move on to the inductance part there. Okay, so you know that one here, the relation between inductance and flux linkages. L equal to lambda by I. Lambda is called as the flux linkages, and lambda is equal to n phi. It's a product of number of turns and flux. Okay, so the unit of inductance is Henry. So simply we can say the inductance as the ratio of flux linkages to current. So this inductance, what we call it as a self-inductance. This inductance, what we call it as a self-inductance. And with the mutual inductance, we have with the M concept. Okay, so M12 equal to N1 D512 by DI1. This is because of 1 to 2. Similarly, for M21, it will be N1 D521 divided by DI2. So from the mutual inductance concept, we have that M12 equal to M21, where M12 is equal to M21. So this concept only will be applied in the transformers. Because the transformers applied in the concept of mutual induction. We can relate self-inductance, mutual inductance with a concept called coefficient of coupling. Coefficient of coupling. So the ratio of total flux produced by the coil to the linking with the second coil, what we call it as a coefficient of coupling. Okay. So here we can see that one. K equal to M by root of L1, L2. Okay. So K value will be always lesser than 1. K value will be always lesser than 1. So K equal to M by root of L1, L2. Where M is the mutual inductance, L1 and L2 are the self-inductances. Okay. Now we can see with the combination of inductors. So in the last sessions, we have seen about the capacitors, combination of capacitors. Similarly, we can see about the combination of inductors. So the inductors we can connect in 2 parts. One is with the parallel combination, another with the series combination. Along with the dot products you will be getting. When you see with the capacitors and resistors, you don't want to see about that part in detail. But here, you will be seeing about that dot products. In the 2 inductors, if the dot is at the starting, then we can say it is series aiding. If the dots of the first coil is the start point and the dot of the second coil is at the end, we can say it is opposing. We can say it is opposing. Depends upon the connection, we can say it as series aiding, series opposing. Similarly, parallel aiding, parallel opposing. Series aiding, series opposing, parallel aiding and parallel opposing. Okay, but for depends upon that we have these four formulae. Okay, but both the inductances are connected in series and add each other, you will be getting L equal to L1 plus L2 plus 2M. Series aiding. Series opposing means L1 plus L2 minus 2M. So whereas when you go with the capacitors or the resistors, simply we will be writing R equal to R1 plus R2. But here we have to consider the effect of mutual inductance effect also. We have to consider the effect of mutual inductance effect also. So we see these formulas clearly here. L equal to L1 plus L2 plus 2M. Here L1 plus L2 minus 2M. Similarly, it comes for parallel connection here. So we can see that one here, a model problem here. The combined inductances of two coils in series is 0.0 Henry and 0.2 Henry. Depends upon the relative direction of current in coils. If one of the coils, when isolated, has self-inductance of 0.2, calculate Knm. You have to calculate Km. So for one connection, if it is series aiding 0.6 and for a series opposing it is 0.1. From that, and also they are given one self-inductance as 0.2. Let us assume L1 equal to 0.2. We can find out L2 there. So after finding out L2, what we have to find out? K and M there. Once you find out L2 from equations 1 and 2, either from equation 1 or equation 2, you can find out the mutual inductance. That's what we have done here. Once you calculate mutual inductance, you can calculate the coefficient of coupling. Coefficient of coupling here. K equal to 0.7217. Then we have the inductance of solenoid. So what is the value of inductance of solenoid? It is given with that formula L equal to mu n square A by L. Similarly, the inductance of toroid. So what is that solenoid? A rectangular coil wound with n number of turns. The solenoid, circular coil wound with n number of turns. So for that, what will be the inductance formula? That and all they are given here. Similarly for the coaxial cable. Similarly for the coaxial cable, you will be having as mu n by 2 pi ln of B by A. So in the last sessions, we have seen about energy stored in magnetic field. Sorry, energy stored in capacitor. Energy stored in capacitor. It is given by the formula of CV square. Of CV square. Similarly, here energy stored in magnetic field is given by the formula. Energy stored in inductor is given by the formula of Li square. W equal to what you will be having of Li square. And energy density, it is mu h square by 2. So it is given by the formula Bh by 2. Mu h square can be written as mu h into h. So you will be getting it as Bh by 2. And we can see that model problem relating with this one. So you have to calculate the inductance of the solenoid, which is of 200 turns, wound tightly on the cylindrical tube of diameter, force is 6 centimeter. Length is 60 centimeter. And solenoid, and that's the permeability is that is the medium is the air medium. If it is ion medium, what will be the inductance? Two cases. One is the air medium, then another medium is ion medium. So first case formula L equal to mu n square A by L. Mu value you know that. Okay, L value is also mu value is mu naught into mu r. Here mu r value is 1. Mu r value is 1 here. Since we have it in that part. So mu naught mu r L square A by L. So substitute that value, you will be getting inductance. If the medium is ion medium, you will be getting about mu r value you have to substitute here. It is not 1. The problem they have given you the mu r value. So substitute that value and find out this part here. This is how we have to solve with the magnetic field. So far we have seen about some of the basic concepts in the magnetic field. In the last 3 classes we have seen about the electric field, and today we have seen about that magnetic field. Any I help you? I know that this data will be somewhat helpful for your gate preparation. Basic formulas, you should know that. Okay, thank you. All the best and thank you.